He is from University of Witwatersrand. He's actually both Bruce and my student, PhD student. And he will be giving a talk on ergodicity and conditional weak mixing on Riesz spaces. Please go ahead, Jonathan.
Hello, well, thank you for the introduction. And thank you to the organizers for this conference. Let's share the screen. Can everybody see the presentation?
Yes, it is quite clear.
Okay, there, thank you. Okay, so yes, I'm Jonathan from University of the Witwatersrand and a student of Prof. Watson and Dr. Kue. And so this work is based on joint work that we did for the PhD. And we're going to characterize ergodicity in a Riesz space and then explore a little relationship between ergodicity and conditional weak mixing. So let's remember, though, that a measure preserving dynamical system in the classical case is represented by the quadruple omega a mu tau. And we'll use the abbreviation MPS because it's going to be lazy to type it all the time. And what we have here is that omega a mu is a probability space, and tau mapping from omega to omega is measure preserving, meaning that the measure of the pre-image under tau of A is equal to the measure of A for each A in the sigma algebra. And then we'll introduce a little notation and say that A in the sigma algebra is said to be tau invariant whenever its pre-image is contained in A itself. And we'll say that an A measurable function f is tau invariant whenever f composed of tau is equal to f. This will play a role in this next slide. So we'll say that the measure preserving system, dynamical system, omega a mu tau, is ergodic whenever the measure of A is either 0 or 1 for each tau invariant A in the sigma algebra. And we get an equivalent definition of ergodicity from the Shields reference here, that the measure preserving system, omega a mu tau, is ergodic whenever each tau invariant A measurable function f is constant almost everywhere. And then there are more results which are established, but I wish to present two, which will be used when we do the generalization. So the first one is there's a theorem which states that, oops, let me get rid of that, which says that the measure preserving dynamical system, omega a mu tau, is ergodic if and only if we have this convergence over here. So we need that the limit of the COSAEF sum of the measure of the intersection of the pre-image of A under tau with B is equal to the measure of A times the measure of B for all A, B in the sigma algebra. So I just want to take note here that we're dealing with intersections of sets and we're dealing with measures of sets and multiplication. So when we move into the Riesz space world, we have some multiplication, so we're going to sort of probably need some sort of f-algebra structure, and we're dealing with measures of sets. So most like, oh, that should be a minus n, not a minus k. I will correct that. Anyway, so we have these products, so we need an f-algebra most likely, and we're dealing with measures of sets. So most likely we're going to need this conditional expectation operator, which is featured over the past week. And then, so the next one is that if we have the measure preserving dynamical system omega a mu tau, we say that it's weakly mixing whenever this condition holds true. So it's the limit of the COSAEF sum. Again, that should be an n. I need to correct that. But now we're taking the absolute value of this difference equal to 0, rather than saying that this measure converges to that product there. These two are going to be key when we look at them. This result is used to define weak mixing. So we need to get a version of this result in the Riesz space to define the weak mixing in a Riesz space. So let's just remember that in a Riesz space E, a non-zero positive element of E is called a weak order unit of E if the band generated by this element is the Riesz space E itself. Then there's another result that if E is a Riesz space with weak order units, now this result comes from the paper by Kuo, Labuskaghni, and Watson on conditional expectations on Riesz spaces. So the original paper on conditional expectations. And this theorem says that in a Riesz space with weak order units, if we have a linear positive order continuous projection, then there's a weak order unit E equal to TE if and only if T maps weak order units to weak order units. So if TW is a weak order unit for each weak order unit of W, we can find this single weak order unit E such that E is invariant under T. We can use this result when we try to prove stuff to make life a bit easier. But the next one is the definition of a conditional expectation operator. And we've seen it pop up many times, but this one I've taken from the original paper. And this statement is that let E be a Riesz space with weak order units. And if T is a linear positive order continuous projection on E with range space, a Dedekind complete Riesz subspace of E, which maps weak order units to weak order units, then we call T a conditional expectation on E, or conditional expectation operator on E. And here, from this original definition, we don't need the space to be Dedekind complete or Archimedean. We just need a Riesz space. But with more structure, things get a bit nicer. And we'll see just now why we need Dedekind complete. Right. So now we're going to make this Riesz space analog of a measure preserving system. So if we look at what happened with the measure preserving system, we can then generate this idea of the analog and then make sure that it is in fact a good generalization by applying it back to the original case. So let's just put it out here. If we take the quadruple ETSE, we'll say that this is a conditional expectation preserving system. We'll use the acronym KEPS because that's easier to say than all of those words. And we need that E is a Dedekind complete Riesz space with weak order units. T is a conditional expectation operator on E. S is a Riesz homomorphism on E. And E is a weak order unit of E with this property that TE equals SE is equal to E. So it's invariant under T and S. And the fifth property is that T applied to S applied to PE is equal to T applied to PE for all band projections P on E. And this is the KEPS is our analog of the measure preserving dynamical system from the classical case. Now, we need this Dedekind completeness. If we go back here, we're dealing with sets which belong to the sigma algebra. And so when we move into the Riesz space world and we take a conditional expectation of a band projection, that is going to, in the L1 case, give us the measure of a set. Now, if we have that E is Dedekind complete, we have the projection property, which means that every band in E is a projection band. And so we have more projections than just the zero map and the identity map, which is good. If we have only the zero map and the identity map, then it's quite useless. That's a trivial case and there's not much to study. So we want there to be more than the zero map and more than the identity map. So by forcing the space to be Dedekind complete, we have that there will be more band projections than just the zero map and the identity map. Okay, then since we have this Dedekind complete Riesz space and we have the principal band generated by E is the Riesz space itself, we can apply Freudenthal's spectral theorem and obtain that the condition TSPE equal to TPE for all band projections on E is equivalent to the condition TSF is equal to TF for all F and E. Okay, now, since we need to move into the world of ergodicity, let's introduce some notation, and which I will pretend that everybody remembers it, but we'll recall it when we need it. So if we let ETSE be a KEPS, then for each F and E and natural number N, we'll adopt the notation that SNF subscript N is the Casaro mean of SK applied to F. And we'll say that LSF is the limit as n tends to infinity of this SNF, provided that the limit exists. And here we're taking the order limit. Then we'll say this is an I, calligraphic I. We'll say that IS is the set of S invariant F and E. So that's F and E such that SF is equal to F. We'll say that this calligraphic ES is the set containing F and E's for which LSF exists. And so we can see that LS maps from this calligraphic ES set to the So we have that this set IS is contained in ES, and in this case, LSF is equal to F for all invariant all invariant F, which means that since LSF is equal to F, we have that F is in the range of this LS, so IS is contained in the range of LS. Then from another paper by Kuo, Labuskachny, and Watson on ergodic theory and the strong law of large numbers on Riesz spaces, Birkhoff's ergodic theorem was presented in two manners, one dealing with the bounded case and one dealing with a T-universally complete case. So I'm presenting here the bounded case with a little bit of rewriting to use our adopted notation here. And this one states that if we let ETSE be a caps, then for F and E, the sequence S and F is order bounded in E, if and only if F lives in this calligraphic ES. So that's the set where LSF exists. And for each F and ES, calligraphic ES, we have LSF is equal to S applied to LSF, and T applied to LSF is equal to TF. And finally, if E, the Riesz space, is equal to this calligraphic ES, then we have that LS is a conditional expectation operator on E with the condition, another property that LSE is equal to E. So this weak order unit E, which obeys TE equal to E, does the same here. LSE is equal to E. Right. Now, there was talk of needing an f-algebra. Let's go back. We're going to be taking some products over here. So we're going to need an f-algebra eventually so we can do some multiplication. So if we let E be a Dedekind complete Riesz space and little e a weak order unit of this Riesz space, we'll say that EE, capital E, lowercase e, is the subspace of E bounded elements of E. And we define it to be, so that should be a lowercase e, whoops. But we define it to be the set containing F and E such that absolute value of F is less than or equal to KE for some K in the positive cone of R, the real numbers. And there are some references to this one all over here, but we have that this EE is an F-algebra. And we'll use dot to be the F-algebra, represent the F-algebra multiplication, and we'll give the structure PE dot QE is P applied to Q applied to E. And then we can take the linear extension of this multiplication and use order limits to extend it to the case of multiplication on EE for F and G and EE. 2, 17, 20, why not? Okay, that should not also be there. So our next note to make about the Birkhoff's bounded ergodic theorem is when we now have this EE. So remember, we have the KEPS ETSE. We can construct this set EE, which is now an F-algebra. And we have, when we restrict our attention to EE, that the sequence SNF is order bounded in EE for each F and EE, which means that EE is contained in calligraphic ES. So ES, calligraphic ES is the set where LSF exists. Furthermore, LSF is in EE, given that LS restricted to EE, given that LS restricted to EE is a conditional expectation on EE. Okay, there's a lot of E's going on over there. Okay, but let's now see when we apply this to the classical case. If we consider a probability space omega A mu, we let E be L1 over omega A mu. We have that E is a Dedekind complete Riesz space. And if we let T be the expectation multiplied by this bold one, then T is an expectation or a conditional expectation operator on the Riesz space E. And this one, the equivalence class of the constant function one almost everywhere, is our weak order unit. And finally, let's say that tau mapping from omega to omega is measure preserving. Then we will define or choose our S so that SF is equal to F composed with tau. So S applied to F is F composed with tau. Then we have ETSE is a CAPS. So giving back exactly the classical condition, what we need. But when we look at this, and we remember there is a definition of ergodicity that the system is ergodic whenever F composed with tau is equal to F for measurable F, only if F is constant almost everywhere. We can rewrite this condition as SF is equal to F only if F is in the range of T, the conditional expectation operator. So this then allows us to define ergodicity on a Riesz space. So we'll say that the CAPS ETSE is said to be ergodic whenever LSF is in the range of T for all S invariant F. So F in IS, so that's the set where SF is equal to F. We can now introduce the theorem that the CAPS ETSE is ergodic if and only if LSF is equal to TF for all S invariant F. And we now introduce, so I didn't put any proofs here because I thought that'd take a lot longer to talk and wouldn't have time to go through the proofs. Whoops. But so we'll introduce some notation now and say that we'll use, with the calligraphic B being the set of band projections on E, we'll use calligraphic P to be the set of T invariant band projections on E. So that is P is a band projection such that TPE is equal to PTE is equal to PE. And we'll let calligraphic A be the set containing S invariant band projections. So P is a band projection such that SPE is equal to PE. Then we'll notice that SPE and PE live in EE for all band projections P. So LS can always be applied to PE and SPE. And we can use this then to establish the theorem that if ETSE is a CAPS, then this calligraphic P set, so the set of T invariant projections, is contained in calligraphic A, the set of S invariant projections, which is equal to some set F, which will define to be the set containing band projections which are invariant with respect to LS. So it's a bit of a characterization theorem here, but we then get the result that the CAPS ETSE is ergodic if and only if T is equal to LS when we have the Riesz space E equal to calligraphic ES. Okay, so now we want to go back quite a bit and remember this result over here. So in the classical case, we had this convergence, or this limit of the COSAEF sum, and we now want to generalize this one to the Riesz space setting. So we'll have that the CAPS we'll consider the CAPS ETSE, and remember that EE is the f-algebra with the multiplication dot given by PE dot QE is equal to P applied to QE for all band projections P and Q. And we'll say we established the result that if ETSE is a CAPS and T is strictly positive, then the system is ergodic if and only if we have this convergence condition. So this convergence condition tells us that the COSAEF sum or the COSAEF mean of T applied to SKF times G converges to TF times TG in order as n goes to infinity for F and G in the f-algebra EE. So we need to restrict our attention to EE so that we can consider F times G. And what we can then do is we can use this result and choose F and G to be band projections PE and QE to get the result that this COSAEF mean converges in order to TPE times TQE for all band projections P and Q on E. Now, this result gives us the generalization of, let's go back, should have written it there. It gives us the generalization of this result. However, there's a little bit more to it. Since we're dealing with a conditional expectation operator, rather than always having here that this is a measure of T minus K A intersect B converging to measure A times measure B, we can now use conditional expectations and we can have conditional probabilities. So this could be measure of a condition to some sigma algebra, some sub sigma algebra sigma. And so this now gives us, in fact, a conditional ergodicity condition rather than the standard ergodicity condition. We can also then, using our result, we can define weak mixing on a Riesz space. And so we have that if ETSE is a CAPS, then the system is said to be weakly mixing whenever this convergence condition is satisfied. So we have that the COSAEF sum of T applied to SKPE times QE minus TPE times QE converges to 0 in order as n goes to infinity for all band projections P and Q on E. And with some more effort, a lot of effort, we can build this result and apply it to general functions F and G in our f-algebra EE. And when we now look at the two results, we have this result for ergodicity, and we have this definition for weak mixing. We can then see that if we have the CAPS ETSE with T being strictly positive, then the system will be conditionally weak mixing. If the system is conditionally weak mixing, then it will be ergodic. Now, a note on why this is conditional weak mixing is very similar, or in fact, the exact same reason. Here we have some conditional ergodicity, where we can take probability condition to a sub-sigma algebra. In the weak mixing case, oops, wrong way. In the weak mixing case, we can take the conditional probability condition to, up here. We can take the conditional probability condition to a sub-sigma algebra. And so this generates our conditional weak mixing rather than just restricted to mu of A. And that brings us to the end of this. And so thank you for listening to that rush talk.
Thank you very much, Jonathan, for a very nice talk. Does anyone have any questions?
Yes, I have a question.
Yes.
Even from the beginning, I miss why is the operator S to be a lattice homomorphism crucial for the definition of conditional expectation?
So are you talking about this lattice homomorphism S? Yes.
Yes.
Okay, so we don't need S to be conditional expectation. All it needs to do is move members or move parts around in the Riesz space E. So perhaps I shouldn't write it like that. All we need here is the condition SE equal to E is crucial, but S itself is not a conditional expectation.
Okay, but also not necessary to be a Riesz homomorphism, I guess. Maybe you can put some weaker condition on an operator S.
So I haven't looked if S is not a Riesz homomorphism. So I'm not sure what would happen if the condition is made weaker. I think perhaps it is something then definitely worthwhile to look at.
Okay.
Okay, so but yes, I don't know the answer to that. So I'm sorry.
Okay, thank you.
Okay, thank you.
Thank you, Nazif, for the question. Anyone else with more questions for Jonathan?
Yes.
Yes.
Yes, Professor Azuzi.
In the fourth condition, fifth condition, you assume that is it equivalent to the fact that Ts is equal to T?
Yes. So that will be the condition then, that Ts is equal to T.
But here you don't need order continuity to obtain
the order so order continuity on S is not assumed. So all we require here is that we have the condition Ts equal to T. We need to impose it though.
I suppose that horizontal theorem is used, then
Yes.
we don't need all the continuities. Okay.
No, not so not for this one here.
Okay, just a second question. For the general definition of conditional expectation, if we restrict ourselves to the classical space, it gives exactly the classical condition expectation. So
yes.
what about what you called here caps?
So for the caps, this conditional expectation operator, it is precisely what's defined. The only reason I require E to be Dedekind complete is that I have more than the trivial band projection. So if I say that the zero map and the identity map are trivial band projections, by forcing E to be Dedekind complete, then I have more than just those trivial band projections.
And my question about S, the map S.
Oh, S.
Do you get the same?
Yeah, you do. And if you restrict yourself to L1,
yes,
this gives you back a classical conditional, and you take T as being your expectation operator.
yes.
Then you'll, in other words, your integral. Then you will get back your classical measure preserving system. Condition 5 gives you measure preserving. For S2 and conditions 3 and 4 give you the type of map that is usually required in your ergodic systems, your dynamical systems. So it breaks down to your classical definition in the case of E being L1, T being your integral or expectation operator, and little e being the constant one function.
Okay, thank you.
Thank you. Anyone else?
One question.
Yes.
Yes, please go ahead.
I'm just wondering, yeah, we're looking at the definition of a KEFs. I'm just wondering, do we need full strength of Dedekind completeness here? Since you mentioned that you're looking for a lot of projection bands in your Riesz space, but can you just get away with just assuming that your vector lattice has the projection property instead of assuming it's Dedekind complete?
Yeah, you can define it all, but the problem is if you actually want to do anything with it, things get, if you take an Archimedean Riesz space, you can still have a conditional expectation operator. But now you start stripping away structure, and all the nice types of convergence Jonathan got later start falling away. So the theory is a lot harder to work with as soon as you start stripping away Dedekind completeness from your setup.
Thank you. Any more questions? No? Great. Thank you very much, Jonathan, for a very nice talk.